Hello, my fellow YouTubers. This is Roy back again. Happy holidays, everybody. We are moving into the Christmas weekend. It's Friday night at the St. Vincent compound. And what do we have here? We're going to do some cool experiments tonight. And it's going to raise a couple topics. Let's just get right into it. So, we're going to test one Ed's theories right now, which Ed says magnets can go through anything. This shows that each magnet is smaller than each particle of light, because he's saying light cannot go through paper or different materials, but magnets can. So let's put the magnets to the test. In order to do this, I'm going to have to put you up on my little holder. And so you can see this. This is the layout of how the magnetic flow is from the end of the prong ends. This is a bolt. This is a ferrite core. This wire is a 16 gauge magnetic wire, and that is north in that direction. Hey Adam, what's up Adam? And that is south direction. And the wire shows the line, we'll call it, of magnetic streams that are running through my workshop. So they're on an angle. Alrighty, so I'm going to put you up here on the holder, and this is going to be some cool stuff, you guys. Let me see what I got to do here. I want to make sure you can see everything. Not really. Let me get a better view here with you guys. So hold tight. You're getting the flipperoonie. All right, so we're gonna turn you around. Hopefully it doesn't screw up your reception. I put you like this, and you're on. Oh, they're strong as shit, so we're dealing with a lot of stuff going on. Can you guys see the wheel? No, you need to be a little lower, huh? Let me get you down a little bit. Think down. That might be better. Alrighty, so we need the compass. Gotta have a compass, right? Where would that compass have gone? Compass. Hang tight, looking for a compass. There's the compass. Alrighty, so got an 1.5 inch thick stock, okay, iron. not shielding. See the compass? You guys see the compass? Not shielding at all. Pretty thick stuff. Inch thick glass. Not doing anything. The magnets are going right through it. Glass is not black. It goes right through glass. We'll use one of Ed's magnetic currents. So many pages. So that's layered. It's going through the book. So the magnetic streams are going through everything. Piece of bismuth. Now I thought the bismuth would have stopped it dead in its tracks, but because it's a diamagnetic, but heck no. Goes through bismuth. So the north and south streams going through so far everything I could find. And we still have a bunch of more stuff to use. Let's see. We're going to go with some layering here. So this is a piece of galvanized steel. It'll just stick. That's not going to do it. It's changing. Going through the galvanized. Piece of aluminum. So we're going to have galvanized and the aluminum still going through. A little on the weaker side, but still going through both of these. Here's some thick rubber. Big old chubby of some rubber. Put that up. Going through the rubber like nothing. Real strong. Rubber, not doing it. Pretty interesting stuff. Over here I melted some bismuth in a metal washer. The metal ring, I thought with the bismuth in the middle would distract it. Nope, goes through it. Piece of pressure treated 2x6. Goes through the wood. Let's get even funkier. You see me reaching over here. Here's a little dielectric thing I made a while back. Copper sheet, plastic tubing, aluminum sheet on the inside. Well, we're going to have to investigate with this because the compass is not even moving. So we have a circle with a void, so I could be too far away. Let me put the compass in here. I don't know if you guys can see that. So it's changing in between these layers. The copper, which is a conductor, and then the aluminum is a conductor. The dielectric in the middle is not shielding it. But space does. But if the magnets were stronger, I'm sure out here would still hit it. Obviously, piece of plastic, we know it's changing in there. So, I don't know. Leave your comments. If you guys can come up with some materials, I can try different metals I have. I have different things so far that I tried to stop it with. Here's a mirror, and the back side is obviously glazed, so it becomes a mirror. And you put the mirror up front, goes through the mirror. Through the mirror, okay? So, mirror's not stopping magnetism. Here's some nickel. All right, here we go again. Same situation. It's not moving again. I'm thinking because of the distance. So let's crunch this up just for yeah, it's still going through. So like I was said, distance on the strength of the magnets does matter, but going through nickel. I got some brass here. Another diamagnetic. Going through the brass. Okay. So, exciting stuff. This is very exciting. Yes, they are, Adam. Got your alloys there. Let's move on to something else, because obviously we're dealing with energy that here, if you want to look past it just being a magnet, okay, it goes through everything. This is stuff that excites me, that it's more than just saying it's a friggin' magnet. Like, I got a bunch of magnets over here stuck to metal, and we all have these magnets, but that's it. So now we're putting stuff to the test. So here, going back to what Ed said in regards to the start of the video, I keep this as my little go-to, and it's always out in front of me. So the bottom we read, magnets can go through, this came out of magnetic current. Magnets can go through everything. This shows that each magnet is smaller than each particle of light. And what he's implying is light can't go through paper. It can't go through wood. There's limits to light. So you would think light is the smallest particle, but it's not. Light is, magnetism supersedes that. The top part here is what we're going to get into right now. He says in magnetic current book, it says magnetic currents are made by concentrating, then dividing, and then shifting the existing north and south pole individual magnets from one place to another. Let's get right to it, guys. Let's go there, okay? So just for shits and giggles, right now we got a V-shaped magnet, okay? So basically one pole is here and one pole is there. Let's get to it. So we got North Pole here, South Pole here. So I also have this lined up as well. If you guys can see the print on there, this says it's South Pole, this says it's North, South, and then North, and so on. And you can see the flow of how the magnetic streams come. They go directly straight across, and they move from north to south, okay? So basically, here's a north. I don't know what's going on, but that was all pulled or thrown out of my hand. That was 3 different things. I think Ed just showed up. Holy crap, where did my compass go? I gotta play that video back later on and watch that. It seemed like everything just got thrown out of my hand. This is crazy. So you can see that, and the magnets are real strong. So you can see that I have it laid out here, and you can see the north street, the end of the north is going always towards the south and always towards the south. So here's one north and south on each side of it. The streams run out, okay? Run out of the north to be wide open, no valve, okay? I'm gonna explain that. What do I mean by wide open, no valve? Meaning the streams are coming out endlessly with no restriction. What we're looking at here is a dipole. So basically we have a dipole with a certain gap here, which is very important. And what we have here is north is chasing the south, okay? And then with the south is on the receiving side. Now what Ed tells us is that the prong ends of the permanent magnets, especially hardened steel, at the ends is where they dam up, okay? So on the ends, we're damming up. So if we're damming up on the north and damming up on the south, now get this, and the north is always going out, and the south is always receiving. That means on the south end, we're damming up here. That means that there's a resistance built in on the dipole. We're talking about a dipole here, it's more than just a magnet, that there's a resistance. And that's where I believe now that that's why resistance is very necessary in the circuit. Like this is a closed loop right here. This is a closed static circuit. It's just a closed loop. We'll just leave it there. A dipole, you have a distance, you have strength, and you have damming up. So basically on the norths are just, we're going to look at them as wide open, full running, wide open, nothing damming up on the ends. On the south side, everything's coming in at one time here. Like, especially here, you got north coming out into the south, the north coming out here, coming in the south. We got damming up going on the prong end. So that's going to create a resistance, which is going to create pressure. And that pressure here, it basically creates the magnetic field, the stream, the strength of this stream that goes by. A cool thing that I was doing with an experiment earlier is I was looking at, okay, here's a south pole, and look, I'm moving the field outwardly. That magnetic field that's running is now part of another loop that's going down. Check this out. So I started messing with the bolts, and we're inside the center of the wheel, and we're creating north and south areas in the wheel, which is affecting a couple things that I want to go over with you guys after I talk about the ferrite. Because these ferrite cores, I never messed with them. I bought them for my Tesla transmitting high frequency. Actually, high frequency. What I didn't know about these ferrite cores is that they are magnetic, okay? And they stick really good. And they actually stick to these two here. But just that it's round, it wants to fall down. But what I realized is when I put up this streamline here for me to have direction, the streamline meaning this wire right here. When I put this wire up, it showed me the direction of my workshop, all right? So once I put the ferrite core, let me get you in a better place. Sorry about that, guys. Once I got into the ferrite core, I realized that there is no magnetism in the ferrite core. And I'm saying to myself, this is mashed up, broken up, fine grit of iron, okay? Why isn't this, if it sticks, why doesn't it, keep any magnetism in it? Because of this. Because it releases it just as fast. So I was thinking about this. This is mainly used in transmission of radio, and especially in ham radio, which they wrap about 14 turns, 12 turns of 12 gauge wire around this, and that's their bandwidth of their frequency. And what's great about using ferrite as a core is that it releases the energy instantly. It doesn't contain it and hold on to it when it's like steel does. And I bet the saturation of this is different than iron. So the other fascinating thing is on this ferrite, when you hold it up, I got to get you guys up a little bit higher. Okay. You guys you're going to love this. When you hold up the ferrite in the angle, I'm glad you guys are back. Having a tough time with this. When you hold up the ferrite in the angle of north and south, all of a sudden the ferrite, you're going to love this, the ferrite all of a sudden has a magnetic field, and it pushes the compass. Let me show you this. This is bullshit. I got this set up here. Hang tight, guys. Just hang tight. All right, here we go. We can deal with that. So we got the compass. You got the line running. When you hold the compass up, let me see. You guys see that whole compass? Nothing going on. There's nothing going on. Watch when we hold it up in line with north and south. Let's see if you guys can see that. Here it is. So when I put it from north to south, the ferrite, I believe it's collecting stream energy into the ferrite core. You can see it's having a magnetic kind of presence about itself. Here you go. All right, here we go. So look, I'm moving the compass. See that compass moving? Look. And watch what happens when I go east-west. It does nothing. Nothing going on east-west. Only when I aim it towards north-south, the ferrite is moving the compass. So that means the ferrite itself is retaining the energy that's moving from north-south in the streams, and it's becoming magnetized. There you go. Look at that. Magnetized. Look. Now, ferrite does not magnetize, but because it's the angle that I'm holding it in, and what I'm assuming is that the lattice structure that's in this ferrite core is in the same angle as the north and south. That's what I'm saying, that I'm thinking is happening right there. Goes to show you. Streams, here's your magnetic north. And there's a ferrite core making the compass react. And when you go the opposite direction, east-west, look, it ain't moving nothing. Got no energy. It's got nothing going on. Fascinating, fascinating, fascinating stuff. I love it. Hope you guys appreciate. Ed left us, but you know what? He says that everything is in those 3 damn books with the pamphlet. You got to mix them all together. So you guys need to get the pamphlets, read into it, and enjoy your comments. Leave your comments, because this is a team effort. This is more than just me. Trust me. But it's me here with the wheel. So it's the help of you guys, the comments you leave. I really appreciate. What I'm going to do on my next experiment, and this is mind-blowing, is that we're going to heat up some of the iron pipe. And we're going to hear it start to have a roar about itself. And then we're going to put a metal sleeve over the iron pipe. And when we move the metal sleeve, we'll hear the roar change and the harmonic change in the pipe. So what I'm thinking here is, you know how it's very easy to heat up a pipe, especially with electric wires. So heat, somehow I'm feeling that thermodynamics, in the sense of electromagnetics, along with the static, there's a whole lot going on here. Whole lot going on. A roar in the fire in the stove. You got it, Tommy. So that experiment's going to kind of blow your mind, because I got a couple of these pipes laying around, couple pipes. And what we'll do is different experiments with different pipes. We're going to heat some up with a torch. We're going to try different sleeves, aluminum, copper sleeves, the same material of itself is, but a bigger dimension sleeves. And we'll be able to move that sleeve up and down. And we'll be able to hear inside of it become harmonic. And we'll know where to put that sleeve on that pipe for harmonics. Exactly, Tommy, vibration, because I was just messing with this before I did the video, and I'm telling you, just now the end of this pipe is shunted, but it's fine. It's just like me shunting this. You get this, guys? That the end of this pipe down here is in the ground and it's shunted. Just like I grabbed this in the U here. So that means we need 2 pipes. Listen, 2 pipes with a pipe connected from one to the other, like making a U. So this whole thing is like a PMH coming up around the wheel. So one side of the wheel is one pipe, the other side is another pipe, and both are shunted to the ground. So that's fine. But when you put both pipes in resonance, you're going to have a lot going on. And we're going to talk about how, hold on, just doing that, touching the pipe. The pipe now, if you can hear that, the pipe is humming in there. Now I'm putting this down. When you get to a certain distance down, you can hear a ring. Pull it out. I love it. There's your acoustics. There's your acoustics. Ed has a sound room at the place, at the Coral Castle. It's where he finds stuff. Yes, it is the same shape. You want to hear something really freaking cool, guys? All right, here you go. Here's Ed's PMH, 2 dimensions. The dimensions of Ed's PMH. Here's the PMH, right? Watch this. I'm going to hold the end like I'm shunting it. This thing is so heavy to hold up. Listen, I'm going to smack the ground with it right now and bring it up. I know you still can hear it, and it's heavy as hell to hold up. So, both pipes. I'm glad you guys can hear it. Both pipes in resonance. With underneath the pipe, we're going to have a static situation. We're going to have a 1 foot square cutout, a foot deep, with 2 layers, something similar to this, where it's going to have a copper, aluminum, and it's going to be in the ground. And this is going to be the 2 plates with a certain gap distance, that every time this gap distance gets loaded up, this is the resistance part I want you guys to understand. When I was talking about these magnets here and how they dam up, and one side's wide open, and so we can have current or flow, and the other side's dammed up, and it builds a pressure in the system. This is going to build the pressure for us. If you looked at some of my old videos, you'll see I was messing with my rubber band static collector, and I was collecting into this. This is just plastic bucket, aluminum outside, aluminum inside. Okay? And I will tell you, shit you not, if you go back to those videos where I had that in there, the pressure built up in that apparatus was tremendous. I'm saying sick off the wall chain tremendous, where I was nervous about it, because not only did it have a good inch of spark, it was fat as my finger. So when I see fatness, that's current. That thing was just ready to go. So that pressure is what's going to help the system between everything. Now, we're still trying to figure all this out, but I got to kind of have a great idea that, yeah, well, Bendini, all I know is just a storyline behind it, that him and his brother died like the same day. Craziness. Who knows what was going on with the Bendini, but we can get into that with a bifilar coil, where I believe that when one side is pulsed, the other bifilar wire is collecting the energy, in a sense like a high power line, where Ed Leedskalnin says that it's the energy's collected in between the strokes. When there's no pressure in the line, it picks up the energy, picks up the electrons, if you want to call them, the negative ions. It picks them up, and then when it's the pressure, when it flips, the pressure hits, it pushes it. Then it stops the pressure and it collects. With Bedini, with the bifilar coil, I believe that's awesome, because you're able to make a coil. You're gonna create AC on one side, and you're gonna create a collector with the other wire. You could probably get even crazier with adding more wires, but one's got to be the transmission line, one's a receiving line, but the receiving line is getting static from the air. A bifilar cone coil, I like that as well. It does have cones, and this is where some things are to come in handy, because if you look at our pictures of the tripod, you'll notice that those boxes up there have little holes at the bottom. Now, they sort of like a sound room would have, in a sense, like a baffle. And it has the two wires coming down to the bottom, and they're touching the stones. So if you're hitting the ground, think about this. When that capacitor I just showed you goes off, it's putting a wave in the ground, and the ground's all connected. So there's a static wave that's penetrating the ground. That wave right there, it's going to go to me, to you, or whatever. It's connected to everything. It's connected to the other side. The static in the ground is the key for transmission. And with Ed's rocks, if you notice that he's popping them out of the ground. Once you pop them out of the ground, I believe he's wetting the rocks down with water, because I believe it's the saturation of water that you're able to control in levitation. For instance, you got hydrogen. You're able to change the molecules. You can overload the molecule and make more of the other molecule, and basically you're flipping the poles in the rock. So you can temporarily flip the pole in the rock by saturating it with water and using the two molecules in the water to be able to make an opposite pole of what it has, and you're able to decrease it. So we're going to try that somehow with an experiment through the process of what we're doing. Other thing I wanted to talk about was how we're gonna create this thing that Ed talks about. Magnetic currents are made by concentrating. So concentrating them, are they concentrated are they dammed up at the ends and concentrated there on the magnets on these ends here? Yeah. But not they could be concentrated more. So what do we need for concentration? There's number one, I should write down. Number two, then divide them, shifting the existing north and south pole individual magnets from one place to another. So we want to now divide them. Well, they're already divided. So basically what we're going to have to create in the circuitry is like a figure eight. So where they're kind of crossing each other, but doing the same thing on the other end. So we kind of want to have another closed circuit that comes off the magnetic part of the wheel. One place to another. So when we get into using the bottom of the pipe as electrostatic collector, there's your separating again. So that would be taking that would be the other end of the figure eight. So the bottom end of the figure eight would be that static collector because you're separating them. And then you're pulling them out of that and you're coming up through the wire in the pipe. The wire tubing that comes through the pipe with the center core. And then you're going to have this pole in the center core, and this outside ring is going to be opposite poles. So you're creating a dipole on top of that pipe. So you can look at the cause being the static collector at the bottom, and the effect is the electromagnetic induction that's going on here. I hope you guys enjoyed the video. Leave your comments. I got so much to go through here that this is getting better and better every time I come in the workshop. I'm trying to see if I left out anything. The other important thing was too, this iron wire here. If let's start off here. So if you look in the wheel, different parts of the metals are picking their own polarization. And I'm asking myself, how is this happening? Like, for instance, these are separate laminated sections that go around here. I think this is like a brake pad that came off the Model T. That's north. That's north. 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 Top of this, north. So everything here is north. This upper ring, which is not connected to anything. There's no continuity or nothing. Showing up south right there. Showing up a little bit east. Showing up south over here. Not even moving. I think when the wheel turns, Ed talks about turning magnets 2,000 RPMs. And he talks about the little metal shavings, how they'll dam up to one side. The other thing I noticed when you spin this wheel real fast, not even that fast, by hand, cranking fast though, that the metal shavings outside the magnets go the opposite way of the turn of the magnets. So if I was spinning this wheel like this, the metal shavings would go over here. And you wouldn't think that. You think they would be over here, but they come over here. We got to do that test for you guys so you can see it. Then if you spin the wheel clockwise, the metal shavings will be on this side. Another topic, another time. But interesting how that centrifugal force comes into play with electromagnetism and basically iron. There's something special, very special about iron. So you could take the handle here, and what I was thinking is that it expands. I don't know if you guys can see that. It expands the pole. So now it's North Pole up top. But the other thing is the iron wire also does. Showing up north on the iron wire right here. So the iron wire here is probably absorbing the magnetism around it, and it's picking up and holding on to it. So someone left a comment in regards to pulsing the iron wire, and that when I put it to my 12-volt car battery, it saturated and heated up everything, and now I get it. So we're going to do another test with pulsing, and we are talking with the wheel moving, and that's right. Mr. Tonic over there. Um, so with pulse in it, the wheel is turning. It's going to have its, I do have built this thing down here. You guys see that? Make sure, so I'm able to turn on and off. And every time this goes by, what it should be doing is dinging, like a vibration in the pipe, like a ding, like a sound. Like basically, every time this thing clicks, inside this pipe, with the copper in there, the core, that thing should be ringing. And just like Tesla's coil should have a harmonic ring to it. It's like pushing a swing, a kid in the swing with Tesla's coil. And the same thing with the two pipes. It'd be like pushing the same thing. And it'll have a frequency, and we're tuning the frequency of the Schumann resonance that's in the ground. And basically, this pipe is vertical. And the vertical pipe will also have a sort of a saturable reactor effect about itself, because it's one in line vertical with the magnetic streams of the earth. So it's already filling up. And once the pipe's excited, like the power line we were talking about, in between when pressure strokes is when it'll recharge itself with free energy, is what's going to happen. That the iron is going to recharge itself. Ed's pipe is 44 inches from the top to the bottom. Here's some stats for you guys. My first visit to Coral Castle, I got my stats. So right here, starter handles 5 inches to the top. So 5 inches long for the handle. The wheel is 7 3/4 deep, meaning from the top of the ring to the bottom. Inside the pipe, 42 inches deep. So I took a tape measure, went down the pipe till it hit something, 42 inches. The pipe inside dimensions is 2 5/8 from inside. 3-inch outside. Outside of the magnets for the whole wheel was 20 inches. The that alternator you see in the picture, it was made from Northeast Electric, Rochester, New York. Still in business. So they can tell you the stats of that generator that he had. At least you know what in current, yada yada. Top of the center round thing, meaning this guy, 5 inches. 5 inches. The inside diameter of the wheel, 10 inches. And I also marked that he has paper or some kind of material, a dielectric of some sort, between gear rings. So he has the magnets isolated from the metal, and he's got some kind of fiber paper that's, I'm using rubber here, double layer. He's using fiber paper. The metal rings are 1/4 inch thick, 1 1/4 tall. There's some good stats for you guys there. That paper's molding away on me. Got to keep it safe. So, all right, guys. Let me see here. Let me see. So, all I can say is one step at a time. key thing here now, I guess, is more experiments, but also time to, I'm going to line all these up perfect so there's no wobble in them, cement them, put the rods inside and have it like he has in his wheel where the north and south, and these are in the cement. You can see that right there, I'm switching it. So what's really cool is that pole will be south right now, south on that side, so that means that's south. You can see it. If you can see it south, then if you switch it over to the other side, then it shows north. So you're moving the streams inside the wheel. And if the wheel is turning, at least at a certain speed, it's going to have centrifugal force inside the wheel itself. And I believe that's going to create some thrust inside the wheel, but we're not fully sure exactly what else is going on inside the wheel. His has been stripped, so there's no telling. But I hope you guys had a good, liked the video, had a good night. Happy holidays, everybody. Peace, love, Jimi Hendrix. And stay tuned. I'll pop out another one. I'm off for 4 days. 4 days off. I'm going to do some damage over here. 4 days. 4 days off. I'm going to kick ass on this thing. I'll start digging in the ground too. We'll get the 2 pipes lined up, and basically we're going to be treating the 2 pipes like a PMH. Bang! Oh my God! You got to go back, watch that video. A couple videos I did with that capacitor that I made. That thing's pressure is so high. It's going to be I'm going to be afraid to be touching anything. But I think the key is to get the wheel self-turning as well. That's why the keeper bars are on here, because when you put the windings on here and increase the magnetic strength when it's pulsed, this pulse will be acting off of this. So when the magnet comes this way, it'll be putting either a positive or a negative pulsing. But that's really more for the PMH. That's really more for this guy that's going to be having a DC. Now check this out. This is crazy. Small voltage DC controls AC's current. So I want you guys to think about that. Think about the satchable reactor in that case. That if we want to control the current, say you could take 110, right, running, and you put small current DC, small DC, all of a sudden you can put up the current or lower the current by how much DC you add to it. We're going to apply that to the pipe. We're going to apply that as well to that PMH you see there. We'll have 2 of those up there, and they're going to be producing the electricity to keep the wheel turning, to keep the system running, self-sustain. We'll just take it from there. You guys have a great night. Peace out. Happy holidays. Over and out.